Continuing with our 7.5 lesson on exponential growth, we left off in the middle of a half-life problem. So for part B, if we have our particular equation, and we do, when will the amount remaining be 20 milligrams? Well, 20 will be our y value. We're just going to have to figure out what the t is. Now, of course, we can divide both sides by 50. And this will just become 2/5. Real quickly, we can take a natural log on both sides so that we're going to be able to bring that t down. And just want to point out a couple of things here. We could use a property of logs and use the subtraction property. It's just as well to divide both sides by the natural log of 1/2 here and get the calculator out real quickly, and we can type in the natural log of 2/5 divide by the natural log of 1/2, and you can see that that left hand side's about 1.321, something like that. And let's just continue up here. Divide, multiply, I should say, by 1,600. And if you do that, you can take this answer, just multiply by the 1,600, and you would get about 2,115.085. And this would be in years. So this is if you wanted a decimal approximation. We could have left 1,600 times this natural log expression, and that would work just fine as well. Let's move on to Newton's law of cooling, our final example of the day. According to Newton's law of cooling, the rate at which an object cools is directly proportional to the difference in temperature between the object and the surrounding medium. Let's let F be the temperature of an object. And the medium might be the room temperature. We'll have F sub m would be that temperature of the surrounding area, the surrounding medium. And the rate at which an object cools, if we were to look at how F is changing, so if we took dF with respect to time, that is directly proportional. So we'd have dF dt equals some constant that we see here, the difference in the temperature between the object and the surrounding medium. In Newton's law of cooling, we're assuming that an object is heated and is then brought into a cooler environment, and then that object will eventually become very close to the room temperature over time. This differential equation will show exactly how this works out. So if an object cools from 125 degrees Fahrenheit to 100 degrees Fahrenheit in half an hour, when surrounded by air at a temperature of 75 degrees, find the temperature at the end of the next half hour. Well, the surrounding medium would be 75 degrees Celsius. So we could write dF dt is equal to some constant times F minus 75. At this point, just want to move quickly and say, of course, F is considered to be a temperature higher than room temperature at this point. Separating this differential equation, we can divide both sides by F minus 75, multiply by dt, and then we integrate. The right side, we could say, is Ct plus some constant k. The left side, of course, we could do a u substitution. If I just gave you 1 over f, you would guess that we'd have the natural log of f, or perhaps the absolute value of f if we needed to worry about that being positive. I'd like to encourage you to think that this antiderivative would just be the natural log of f minus 75. We're assuming that f is above 75, and I think you can quickly check with the derivative that this is in case true. What you can also notice is whenever you have f plus or minus some value down below, as long as that denominator is positive, that antiderivative would be the natural log of f plus or minus that constant. So at this point, we're going to exponentiate both sides. We'll take e to the left side, we'll take e to the right side. And I think it's pretty quick to notice the left side becomes f minus 75. The right side, using a property of exponents that we talked about before, we could think of this as e to the ct times e to the k. Normally we'd start with something like this and then combine by adding the exponents. Right now we're just really working backwards. And I'd like to then also just point out that e to the k can be moved out in front. Next, I'll add a 75. And at this point, I just want to say that we need to find e to the k, and we need to find out what e to the c is. And the way you do that is you use your initial information. The temperature starts off at 125. So when t is equal to 0, f is equal to 125. Let's go ahead and do a little bit of work plugging that in. And, you know, when you have c times 0 up here, that's a 0 itself. And e to the 0 is just a 1. Okay, e to the 0 collapses to a 1. I can subtract a 75 from both sides here to get 50 is equal to e to the k. That means that this equation that we have up here, we now know what e to the k is. It's 75 plus 50 times e to the ct. Well, at this point, we're a little bit closer. We know that this object is cooled to 100 degrees. Temperature is dropped when t equals half an hour. So I can plug in 100 for my f and then continue to work and see if we can finish this up. I'm going to subtract a 75 to get 25 is equal to 50 times e to the ct. And then we can divide both sides by 50 to get 1/2. And forgive me, I forgot to plug in this 1/2 here. That's very important. We can essentially say now that we have e to the c times 1/2 is equal to 1/2. Well, what I'd really like to do is solve for e to the c. So what we can do on both sides right now is simply square. And when you square, 2 times 1/2 is just going to be a 1, so you'll just have e to the c. Now right now, just want to point, look at the very top of the screen here. We had f is equal to 75 plus e to the k times e to the ct. We found out what e to the k was. Here's in the middle of the screen. We then could write f is equal to 75 plus 50 times e to the ct. Right now, we know what e to the c is, so we can get even more specific and say e to the c is really 1/4. And here you have it, a nice, simple equation where you have all of your relative data. You now have all of your specifics. This is, in all truth, what Newton's law of cooling is really going to look like. They said, what would be the temperature 1/2 hour later. Well, we knew that F was 100 at a half an hour after cooling. A half hour later would be when T equals 1. You already had a half hour to cool down to 100 degrees Fahrenheit. A half hour later means that it will be 1 full hour after you have cooled. So let's go ahead and plug that in. We'll have 75 plus 50 times 1/4 to the 1. And if you work that out, 50 divided by 4 is actually going to be 12.5. And if you just add 75 plus 12.5, you'd get 87.5 degrees Fahrenheit at T equals 1 hour. So now we can answer that specific question. Okay, I hope this helps. Best of luck to you.